All right. Hey guys, just thought I would stop in and give you a couple quick things that might help you on the homework for Monday. It's not a particularly difficult topic, and you can certainly read it in the book, but sometimes people prefer to watch a presentation. So I kind of put it up here, and just it looks like there's a lot on the board, but it's mostly just examples of things, and it's really not that deep. So I'm going to go quickly. Just to show you some of these matrices. These are types of matrices that come up a lot. 7 different categories here that are worth kind of being really familiar with. Okay, in almost all of these cases, we are only going to be talking about these concepts for square matrices. So I said n by n right here. Okay, so most of these concepts don't make sense if you don't have a square matrix. So in class on this past week, I talked about symmetric and skew symmetric matrices. So just to review really quickly, symmetric matrices are equal to their own transpose. And it just means that the ij entry of the matrix is the same as the ji entry of that matrix. I drew an example here of like how it would look using the general variables like A, B, C, and then B, D, E, and then C, E, F. The idea is that across this main diagonal, which we called it, everything reflects, and it looks kind of like a mirror. So the B's, the C's, and the E's reflect across the main diagonal. A, D, and F can be whatever. Okay? And this is just a 3 by 3. Of course, it could be 4 by 4, 5 by 5, and you might need more letters to describe it. But this is just an example. Skew symmetric matrices are very similar. This time A transpose equals negative A, which just means that the ij entry is the negative of the ji entry. Here's a 3 by 3 example of that. Notice the zeros on the main diagonal. For a skew symmetric matrix, you must have the zeros on the main diagonal. So there are zeros on the main diagonal here. And then across the main diagonal, the numbers are the negatives of each other. So these are kind of negatives like that. Okay, and that will always be that way for a skew symmetric matrix. The reason you have to have zeros along the main diagonal is that if you take the transpose of the matrix, which really flips it across the diagonal, the entries have to become negatives of each other, because the definition of a skew symmetric matrix is that A transpose equals negative A. Okay, so we talked about that already before. Here in the middle, another family. These 3 kind of go together as well. Upper triangular, lower triangular, and diagonal matrices. Upper triangular matrices, I drew a 4 by 4 example. The key thing here is that the area below the main diagonal is all zeros. Above and on the main diagonal, you can have any letters you like, any numbers you want. When I put a letter in there, it means it can be any number I like. So there could be more zeros up here too, but that's not required for an upper triangular matrix. The key thing is you must have zeros below the main diagonal. Here's the condition. Aij has to be 0 if the I is bigger than the j. So if I'm in a lower row than I am column, that's going to put me down here in the lower left part of the matrix. That has to be 0. Okay? Lower triangular matrices, I drew a 3 by 3 example. It's the opposite. Now all of the entries that are free are on or below the main diagonal, and the entries to the northeast or above the main diagonal must be 0 in this case. All right? If you put the 2 together and you have a matrix that's both upper and lower triangular, you're going to get what's called a diagonal matrix. These are the most simple matrices that you could ask for. You have numbers on the main diagonal, which may or may not be 0, but off of the main diagonal, in other words, if I does not equal j, the entry aij must be 0. These matrices are going to come up a lot. They are very important, and they are very simple. And so we want to make sure that we know about those. Okay? So those 3 kind of go together. Upper triangular, lower triangular, and diagonal matrices. Lastly, over here, we have the zero matrix and the identity matrix. The zero matrix kind of behaves the same way that the number 0 does, and the identity matrix kind of behaves the same way that the number 1 does, in the following sense. So the zero matrix is just all zeros. And that one doesn't have to be a square matrix, so I wrote here, it could be an m by n matrix. We often just put the size right here as a subscript on the 0. If it is a square matrix, we just usually write the size n, so 0 sub n. It's just a matrix of all zeros. When you add that matrix to any other matrix of the same size, you just get that other matrix again. So the zero matrix is like 0. It just, when you add it, it's like doing nothing. Okay. The identity matrix does have to be a square matrix. It does have to be square. So we write it as I sub n, and it's really just a diagonal matrix where you have 1s down the main diagonal. So all the diagonal entries are 1. Here's the description of it in terms of the Aij notation. Oops, let me get that off of there. So Aij is either 0 or 1, depending on whether you're talking about the diagonal elements or not. Turns out that when you do matrix multiplication and you multiply this matrix by another matrix, it doesn't change that other matrix. That's why I said that the identity matrix kind of acts the same way that the number 1 does. So anyway, we're going to be using these matrices a lot this semester, and I just thought this was a great time to just kind of summarize it really quickly. The symmetric and skew symmetric ones, those kind of go together. Upper, lower, triangular, and diagonal matrices, those kind of are the same general idea. And then the 0 and identity matrix is like the 0 and the 1. Those two matrices are often thought about together. So we kind of have 7 different categories here, and those are most of the special matrices that we're going to see this semester. And I just thought it would be good to summarize them for you. Okay, hope that that's helpful, and I will see you guys soon. Thanks.